A bipartite graph is a graph whose vertices can be split into two groups. Every edge must go across the split, never within the same group. This shape appears in matching style problems, people to jobs, students to courses, users to items, or tasks to machines. A triangle is the smallest warning sign. If you try to split it into two groups, one edge always ends up inside a group, so it is not bipartite. The usual test is two coloring. Pick an uncolored node, color it blue, and put it in the BFS queue. When BFS visits a node, every uncolored neighbor must get the opposite color. So from A, nodes 1 and 2 become green. Now process node 2. Its uncolored neighbors B and C must be blue, the opposite color from 2. Process C next. Its uncolored neighbor 3 becomes green. For every edge, the endpoints now have opposite colors. Since no same color edge appears, this component is bipartite. Odd cycles are exactly where two coloring breaks. Start with a triangle, and color one node blue. Both neighbors of that blue node must be green, because every edge needs opposite colors. But the two green nodes are also connected to each other. That edge has the same color on both ends, so the coloring is impossible. This is why a graph is bipartite if and only if it has no odd cycle. A triangle is the smallest odd cycle. One of the main reasons bipartite graphs matter is matching. Think of the left side as people, and the right side as jobs they are allowed to take. A matching chooses edges, but no vertex can be used twice. So if A is matched to 2, then B cannot also use 2. A valid matching keeps the chosen edges disjoint. Here it takes 1, B takes 2, and C takes 3. This scene only defines the matching idea. Finding a maximum matching is its own algorithmic problem, handled by algorithms like Kuhn or Hopcroft-Karp. The two-color test runs in O of V plus E time, because every vertex is colored once and every edge is checked. The extra space is O of V for the color map and the BFS queue. Define the bipartite test on a graph. Create an empty color map. Loop over every vertex, because the graph may have multiple components. Skip vertices that already belong to a colored component. Start a new component by coloring this vertex 0. Initialize the BFS queue with that start vertex. Continue while the queue has vertices to process. Remove the next vertex from the queue. Check every neighbor connected to this vertex. If the neighbor is uncolored, give it the opposite color. Then add that neighbor to the queue. If the neighbor already has the same color, the two-color rule failed. Return false immediately for that conflict. If every component finishes with no conflict, return true.